So welcome back. We're going to move into a new discrete probability distribution. Very important one. We refer to this as the binomial probability distribution. So it's basically one of those probability distributions that are very useful, and it is associated with a multi-step experiment that we call the binomial experiment. So as the name suggests, a binomial experiment basically has two possible outcomes. So first of all, you have a sequence of n identical trials. You have a sequence of n identical trials. So an example of such a situation is when you have, for instance, when you are tossing a coin. So each time you flip a coin, each trial is identical. If it's an unbiased coin, then each trial is identical. There is no reason to believe that the conditions have changed between the first, the second, and the third attempt. Yeah. So if you have a situation where you have n identical trials, and then you have two possible outcomes, like the situation we have with an unbiased coin, you have a heads or tails. And then thirdly, the probability of a success, which is denoted by P, does not change from trial to trial. So that means that trials are independent, yeah? Trials are independent and the probability does not change from trial to trial. So if you have these four conditions, then you have what you call a binomial probability distribution. So this number 3 is what you call the stationarity, requirement, the stationarity constraint. It is possible in some situations that you could have four where the trials are independent, but the probability is affected by some other thing that has nothing to do with the trials, and meaning that you're going to have different probabilities between different steps. But if you have these four conditions, you have what you call a binomial probability distribution. So again, it's going to be a discrete probability distribution because it is possible for you to actually enumerate all the possible outcomes. Case in point, when you're tossing a coin, it meets all the requirements for a binomial probability distribution because you can actually enumerate the entire sample space. You can actually define the sample space exhaustively. So this is basically what I've been talking about. So if you look at the coin example, if you want to count the number of heads appearing over 5 tosses, so if you want to count the number of heads appearing over 5 tosses, we can actually enumerate this result. Yeah, we can actually enumerate this result, and because of that, we refer to this as a binomial experiment. So it does turn out you can actually have a very neat formula to express this, because when you want to find the number of heads that you get when you toss a coin 5 times, maybe some of you can see that this is very similar to a combination problem. This is basically a combination problem. This is exactly the same problem. It's exactly the same question if I asked you how many different ways, yeah? How many different ways can you pick X samples from a space of 7 samples. For instance, if you have 7 people and you have only 5 chairs and you want to find how many different sitting arrangements. So this is precisely the same problem that you have. It's basically a combination problem. So you can find out, for instance, if you want to find the number of heads appearing over 5 tosses, so where heads is what we refer to as a success, then this is basically a binomial distribution. So like I said, property 3 is what you call a stationarity assumption, and there are some situations in which it does not hold. For instance, if you are a salesperson and you are trying to, you are reaching out to customers, customers could sign on to your program, or customers could make a purchase with some probability, and then they may not make a purchase by 1 minus that probability, right? Say there's the probability is like 0.4. In this case, the probability is going to be, well, it's not mentioned here. Yeah, so it is possible that customers will take on a product with a probability of 0.4, and they will not take the product with a probability of 1 minus 0.4, which is 0.6. Because in a binomial experiment, remember, you have mutually exclusive outcomes. So the probability of one is 1 minus the probability of the other. And the trials are independent, right? Because the probability that a customer buys a product is not going to depend on whether the last customer I spoke to bought a product, yeah? But there could be some other internal process. For instance, I may get tired, yeah? If I get tired, then my conversion rate could actually be less in the afternoon, for instance. So in this case, subsequent trials do have a different probability distribution, right? They do have a different probability function. So if I have a situation like that, if I do not have property field, what you call a stationarity constraint, then it ceases to be a binomial probability distribution. But like I told you, it's very the result for probability distribution function is probability the binomial discrete probability distribution is going to be very similar. The calculations are going to be very similar to the calculations that we had when we were going over counting rule for combinations. For instance, basically what you normally track in a binomial experiment is the number of successes, yeah? The number of successes. If I go back to the coin experiment, and for instance, I can define the number of heads as the number of successes. So I can have an actual formula that describes the probability that I get exactly 3 heads, yeah? So the probability that I get exactly 3 heads, so in this case, probability is given by this formula, which I do not like very much because it is really a combination, and this looks more like the notation that we used for permutations in chapter 4. But if you ignore that, you can see on the right hand side, this is essentially a combination, right? This is essentially a combination. So if I have n trials, if I have 5 tries and I want to find out what is the probability that I'm actually going to get 3 heads, I can actually calculate this directly, because then the n is going to be 5 and the x is going to be the 3. So it's going to be 5 factorial over 3 factorial into 5 minus 2 factorial, or which is 5 factorial over 3 factorial into 2 factorial. So essentially, if I want to know the number of, the number of heads in 6 coin tosses, so it's going to be, it's basically going to be, so what is n? Yeah, n is the number of trials. So n is equal to, just a minute, number of trials with exactly 3 heads in 6 trials. The number of, okay, it's very confusing because I'm using the word trials twice, so I'm trying to see what other word could I use. Number of outcomes, yeah, so basically number of outcomes with exactly 3 heads in 6 trials. So n is going to be 6. So x, what we refer to as the number of successes in the jargon, and the usual statistical jargon, is going to be 3. So this is really a combination. So this would essentially be the same thing if I was asking how many different ways. If I asked how many different ways can I pick a team of 3 from 6 players? So it's exactly the same kind of question, because essentially what you're doing is you're trying to see how many different ways you can pick 3 heads out of 6 tries, yeah, out of 6 possible positions. So it's really the same kind of situation. So it's going to be, so it's like we said, it's n factorial over, let me use the formula notation so you can have a very, so if I use the formula notation, just have a new equation, then insert so that it looks I want it to look good. So we said you could just insert a new equation here in Word. So you want to have a, so it's basically a fraction. It's a bracket. So you want this one. So we said it's going to be x from n. Yeah, I think that's how you read it. You say x from n is basically going to be a fraction, and on top of that fraction you have n factorial, and then you have x factorial into n minus x factorial. So what this becomes for us basically is going to be, because we have n is 6 and we have x is 3, so the number of outcomes that have exactly 3 heads is going to be, so our n is actually 6 factorial. Let me just get the fractional notation. So we want one of these, right? So we have a 5 factorial over, or we say 6 factorial, right? Because we have 6, right? So it is 6 factorial. What am I doing? So we have 6 factorial into 3 factorial into 6 minus 3 factorial. So that's 3 factorial into 3 factorial. So that's basically 3 factorial times 3 factorial. So 6 factorial is what? 6 factorial is actually 6 by 5 by 4 by 3 factorial, right? I don't need to flesh out, so we could immediately get rid of this. So this becomes, so if you get rid of this 3 factorial part, remain with 3 factorial, which is basically 3 by 2 in the numerator, which is basically 3 by 2. That would give us what? That gives us a 2. You get rid of that 3, and that gives us another 2 up here. That gives us another 2 up here. And we can get rid of this altogether. So we basically have, according to this, we have 20 different ways that we could come up with 3 heads. Yeah, we have 20 different ways that we could come up with 3 heads. So you can actually compute the actual value. You can actually compute the actual value from this. So this is basically the and then if you wanted to get the actual probability of this, yeah, remember this is essentially an independent event, yeah. So if you have to get the probability of an independent event in a multi-step experiment, then you have to multiply by the number of you're going to multiply by the number of tries, but the probability P is the probability of a success, right? And so that means the opposite, in this case a success is a head, right? So if this doesn't happen, the opposite is going to be a tail, right? So 1 minus P is going to be the probability of what we shall call a failure, yeah? The alternative outcome. Remember, there's only 2 outcomes because it's a binomial distribution. So the alternative outcome or tail is going to be 1 minus P. So because this is an unbiased coin flip, it means that the probability is 0.5. So that means 1 minus P. So a probability of a head and of a head or tail is the same. Probability of a failure or success is the same, yeah? So this value over here gives us the probability, that gives us the number of, yeah, the number of events in which we get 3 heads, yeah? So if we actually wanted to get the probability that we get a head, probability of a head, Yeah. Remember, since these are independent events, we could simply use the product rule of probability. This is the value this is the number, so this is the value. So if we're going to use the product rule, it means, it means that the formula actually for getting the probability is going to be that combination that we have over there. Let me just insert a new equation over here. So I'm just deriving this, then we shall check back and see if it is actually the correct formula. So it's going to be that combination, it's really that combination, and then you're going to multiply this by the probability of getting a success, right? The probability of getting a success. And that would be, the success is going to be, so, because if you have a sequence, let me just do this again, yeah? So if you have some sequence of this sort, we have 6 tries, yeah? So you could have something like this, 1, 2, 3, 4, 5, 6, right? So this is one of the sequences that you could actually generate. This is one of the sequences you could actually generate. But we're interested in sequences which have 3 heads. So it could be something of the sort. It could be something of the sort. You have 6 outcomes, right? It could be something of the sort. Oh, sorry, you've already seen that. It could be something of the sort, and so on and so forth. So basically, the probability of every situation, the probability of every sequence in which you have 3 heads is going to be more or less the same, because you get a probability of that by that by that by that by that, and then it's going to be basically the if you use the product rule of probabilities, in each situation it's going to be, in this case it is a half, right? In the first try it's a half again, a half, a half, a half. So it's basically going to be that 0.5, right? 0.5. So a probability of every single sequence is going to be that 0.5 to the power 6, right? It's going to be that 0.5 to the power 6, right? So it's essentially the same thing that we do over here, because we know that probability is going to be 0.5, but I can expand this out really to make it the probability of heads in this sequence to the power of probability of tails in this sequence, right? Which is really, in this case, it still works out to 0.5. It still works out to 0.5 because it's an unbiased coin to the power. But if we had the probabilities, if we calculate the probabilities of heads separately, it will be probability of that by that by that, which would be 0.5, 0.5 to the power 3 multiplied by, if you calculate the probabilities of tails separately, it's going to be by 0.5 to the power, again, so here it looks a bit redundant. So basically it means, what we do in the formula is exactly this, we flesh it out. So in this case, the probability is the number of heads that we want, which is the successes, right? Into 1 minus, so this is now the probability of the alternative outcome raised to the power to the power n minus x, right? So this is basically going to give us the probability of a binomial experiment. So this expanded version is important, especially because sometimes you have an unbiased, a biased situation. So for instance, you could have a biased coin where heads occur with a probability of 0.2 and tails with a probability of 0.8. So that means we can, because if you had an unbiased coin, this would really be the same as of doing this to the power n, right? But because you have to assume in some situations you'll have bias, so this really gives it a probability of obtaining x successes, right? In a binomial experiment. So you're basically getting the probability of a single event in which you have x successes, and then you're combining those events because the sample space for that event has got this number of sample points, right? So let's just look through the formula. So basically, this is the formula I told you about, where you have the number of events that will give you a particular sequence, a particular number of successes, and you can see it's basically the combination counting rule. So probability of a specific event is this. So this is the thing that we have in this side of the equation. It is basically that of any sequence is going to be that, and this comes directly from the product rule of probabilities. And then if you are then going to sum up the actual probability, if you are then going to sum up the actual probability for all events in which you have X successes, right? Then you have to get this value over here, this thing over here, which is the combination, because you're getting all events, So, and this is the number of events that will give you X successes, right? Then when it comes to the expected value, is pretty straightforward. It is the number. So this is the mean of a binomial distribution. Is basically the number times the probability of a success, right? So this will give you the mean of a binomial distribution, right? And then the variance is given by this formula. So you can actually do this and work it out if you're really inclined. If you're interested in the actual math and you can actually derive this value. But then finally, I want to talk about a Poisson distribution. Maybe to take you back to this. So in general, well, there's not a lot of discussion here. Maybe, well, I think I've forgotten what I wanted to say here. Maybe it is not very important. But let's move on to the Poisson probability function. So a Poisson probability function is given by let me just go back to the slideshow from a current slide. So this is the Poisson probability function. So a Poisson probability function, so it's given by this formula. I'm not going to go into the formula too much. This will be supplied. If there's a question about Poisson probability function, this formula will be supplied. But the formula is actually derived directly from binomial distribution. It is actually directly derived from binomial distribution. So a Poisson probability function is actually what you get if you assume if when n tends to infinity in the when n tends to infinity in the binomial probability function, then you get the Poisson probability function. So for those of you who are mathematically inclined, you can check out the proof. There's a bunch of YouTube videos where you can check this out. But anyway, do not worry too much about the formula. It will be provided. But what you have to understand is that you have to first of all understand what this is and why it is important. So basically, it's very useful if you're defining the probability of an event, of a random event, when time and space are involved. When time and space are involved, especially if you make the assumption that the probability of events within equivalent time periods is going to be the same, or equivalent space intervals is going to be the same. For instance, suppose we're interested in the number of arrivals at a drive-up teller window of a bank during 15-minute period, or this could be a number of arrivals at KFC, for instance. So if you're interested in the number of arrivals at KFC within a 15-minute period, then if we assume that the probability of any consecutive arrivals is independent of each other, but the probability of arrivals, the number of arrivals within equivalent periods is going to be more or less the same, then you can apply a Poisson probability distribution. So first of all, you have to make the assumption that probability of a car arriving is the same for any two time periods of equal length, and that the arrival or non-arrival of a car in any time period is independent of the arrival or non-arrival of any other time period. So this would basically form the basis for a Poisson probability distribution. So if we make this assumption, and then we, for instance, at Bell Labs, we are trying to model, if at Bell Labs we're trying to model the distribution, the probability of these cars arriving within this 15-minute period. And our historical analysis shows that the average number of cars arriving in a 15-minute period is 10. Then we can apply the Poisson probability distribution. In this case, mu is going to be, yeah. So if you want to find the probability, for instance, that 5 cars arrived, yeah. If you want to find the probability that it was 5 cars that arrived within this 15-minute window, then mu is the observed average, which is 10, right? Mu is the observed average, which is 10. Then x would be the number of successes, which is 5, right? So it is going to be 10 to the 5th. Then you have this exponential to the minus of mu, to the minus of 10 over x factorial. So this is basically will give us the probability that exactly 5 cars will arrive in a 15-minute window. So if you're really interested in the formula, like I said, this is a direct result of a binomial distribution. So if you have a binomial distribution, then over time it will yield. If you want to look at those events as a function of some interval of time, it will basically yield a Poisson probability function. So that basically ends chapter 5. So I'm going to be, if you have any questions, as usual, you can reach out to me via WhatsApp. But this is basically the end of chapter 5. As usual, there are exercises in the book, which I'm sure everybody has by now, because it was the first order of business at the beginning of the semester. Then you could try out the exercises, and then there are solutions at the end. Yeah, but if you have any issues, then you can always reach out to me via WhatsApp.